Hello all, good morning. Welcome to Unacademy. Today we will going to see our next lecture on discrete mathematics. In this lecture we will see the group studies, the group theory in how to solve the examples on group theory that we will see in this lecture. Okay. Now let's start. Before going to start this, let me introduce myself. Myself Dhanashree Mam. I completed my MSc in mathematics from Mumbai University and also having 13 plus years of teaching experience. And I mentored more than 10,000 plus students for the engineering. Next. Before going to start this, I will tell you how to install the Unacademy's Learning app. First, go to your mobile's Play Store app and then search Unacademy's Learning app. After that, install the Unacademy's Learning app. And then here step 3, manage your goal. जैसे कि हम लोग यहाँ पे अभी GATE and ESE के लिए manage कर रहे हैं, so you can manage your goal as per your requirement. And here you can choose your subscription plan, either for plus subscription, free courses, special classes. It is up to you. And here put the get subscription button. Press the get subscription button icon here. Now see, here you can select the subscription plan for GATE and ESE for 24 months. Okay, either for 24 months or for 12 months. And to get the 10% discount on your subscription fees, you can use my promo code, that is DSP, and you can use any one of this payment method, either debit card, credit card, EMI, UPI or wallets or net banking. Now, here most important thing I'm going to announce you here. Yes, you can crack the GATE. Top educators coaching here live on Unacademy. Sparks for GATE 2022 for batch A. Here बहुत सारे जाने माने आपको चेहरे दिख रहे हैं. Okay, जैसे कि अंकित सर है, बाय रेड्डी सर है, शंकर सर है. Okay, and many more are there. And the English batch starts from the 18th January for electrical engineering. Okay, so the top educators coaching here live on the Unacademy. Now next is the next for 2022 for Sparks for the GATE 2022 batch A. It is also start from the 18th January. Okay, for ECE, and work for the GATE 2023, that is for ECE batch A, English starting from, again it is from the 18th January, and early start extra age. Okay, now work for the GATE 2023 here, electrical engineering, so batch A English starting from 18th January, so you will get early start, early age. Now to unlock any free plan of Unacademy, you can use my promo code, that is DSP, for the special classes, live test series, quiz and Unacademy combat. Okay. Let's start our actual topic, that is group theory. Okay, here we will see group theory. In the group theory, the definition of a group, then how to find out the how to show that the given set with the given operation forms a group. That everything we will see in this lecture. Now see, what do you mean by binary operation on a set? Let G be a non-empty set, then G cross G is equal to AB, ordered pair AB, such that A belongs to G, B belongs to G. Then if F defined from G cross G to G, then F is said to be a binary operation on the set G, and star is a binary operation. Binary operation, it means what? It will require at least two elements. So that operation you have to operate on the two elements. For example, addition, subtraction, multiplication, division, all are binary operation. And the special binary operation also we can define, that is star. It is depending upon example to example. So we will see that the binary operation on a set G. Here, let G be a non-empty set. Then G cross G is equal to ordered pair AB, such that A belongs to G, B belongs to G. And if F defined from G cross G to G, then F is said to be a binary operation on the set G, and star is a binary operation on set G if and only for all AB belongs to G, A star B also belongs to G. Now, here we will see that, see, if star is a binary operation on the set G, then A star B is a unique here. We can see that A star B is unique. So here a binary operation on set G is known as a binary composition. Okay. Here binary operation is known as a binary composition. Now see, let A is equal to closed interval 0, 1 is a closed under multiplication and addition. That we will see here how we denote the binary operation. And let A is equal to 0, 1 and is closed under multiplication and addition. Okay, so we will see here closed under multiplication and addition. Let A be the set is given as, see, suppose here is 0, here is 1, here is 0, here is 1. We will see the composition table. So here addition, multiplication and addition. So first we will see multiplication. Okay, no issue. So we will see the multiplication or dot here. So 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0 and 1 into 1 is 1. Okay, and for the addition we will see here, for the addition here 0, 1, 0, 1. So you will get 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1, in this 1 plus 1 is equal to, here is 1. Okay, so we sorry, 1 plus 1 is equal to here 2, right? So plus and dot, both the operation defined on a set A. Now if you see, this is a binary operation. Okay, this is a binary operation on a set A, addition and multiplication. So A is closed with respect to 0, with respect to dot. Here A is closed with respect to dot. Why it is closed? Because every element from this set, so the composition tables, every element from the set A only, therefore dot is closed, right? Dot is closed, or here we say that A is closed with respect to dot. In that way also, A is closed with respect to dot. Okay, now here we can see that the this element 2, which is not present in set A, right? 2 is the element which is not present in set A. So A is not closed with respect to addition, because every element is not from the set A only. Therefore A is not closed with respect to addition. A is not closed with respect to addition. Okay, here A is not closed with respect to addition. So this set A is not closed with respect to addition, and A is closed with respect to multiplication. Okay, this is your binary operation. Now see here, what do you mean by algebraic structure? Okay, let's see the algebraic structure. What do you mean by algebraic structure? Algebraic structure. A non-empty set G, a non-empty set G equipped with a non-empty set G equipped with a binary operation, a non-empty set G equipped with a binary operation is called as an algebraic structure. Okay, a non-empty set G is equipped with a binary operation, then it is called as an algebraic structure. A non-empty set G equipped with binary operation, is called an algebraic structure. Is called an algebraic structure. Here we can see that suppose star is a binary operation, then G star, suppose star is a binary operation on set G, then G star is a algebraic structure. Okay, G star is a algebraic structure. Now, next we will see, so there are many algebraic structures. For example, suppose n is the set of natural number and addition is a operation, binary operation defined on set of natural number. So n plus is a algebraic structure. N with respect to subtraction is a algebraic structure. N with respect to multiplication is a algebraic structure. N with respect to uh, any defined operation star is again a algebraic structure. Okay, so there are many algebraic structure here we can see. Now see, the every time this is closure property, so we'll see the closure property. What do you mean by closure property here? So closure property, it means if we take any two elements for A, B belongs to G, then A star B is also belongs to G. Then we say that G is closed with respect to star. G is closed with respect to star, right? G is closed with respect to star. Then we say that G is closed with respect to star. Now, next is suppose here we will find out the closure. G is closed with respect to star. So here we can see, here we'll see G is closed with respect to star. Now, the next operation, that is associative property. That, so for example, we will see the closure property here. Suppose if we take a set of natural number with respect to addition, right? If we take set of natural numbers with respect to addition, then here set of natural number with respect to addition, so natural number is closed with respect to addition. It means if we take any two natural numbers, suppose 1 2 belongs to set of natural number, then 1 plus 2 is equal to 3 is also belongs to set of natural number. Therefore set of natural numbers is closed with respect to addition. Okay, set of natural numbers is closed with respect to addition. Here we can see. Now, next property, that is associativity. Everything we will see here. Now see, a group. First of all, we'll see the definition of a group. What do you mean by group? A non-empty set equipped with one binary operation star. This is very important. It is equipped with only one binary operation star is called a group if star satisfies the following postulates. So which are that postulates? First is closure property, second is associativity property, third is existence of identity, and fourth is existence of inverse, and fifth is commutative property. Okay, so we'll see the closure property here. For all A and B belongs to G. So A star B is equal, A star B belongs to G. So associativity property here, we can see that closure property for A B belongs to G, A star B belongs to G, and associativity for all A B C belongs to G, A star B star C is equal to A star B star C, right? A star B star C is equal to A star B star C. It means we will see example of each and every element here. Third is here we will see set of natural number with respect to addition is closed. Okay, so here binary operation is addition and the set G is equal to set of natural number. So set of natural number is closed with respect to addition. Okay, next, associativity property. For all A, B, C belongs to G, so A star B star C is equal to A star B star C, right? So for example, here we have seen, first of all, suppose if you take 1 plus 2 is equal to 1 plus 2 is equal to 3, which is also belongs to set of natural number. So set of natural number is closed with respect to addition. Now associative property for A, B, C belongs to G here. Okay, so we'll take, suppose 1, 2, 3 belongs to set of natural numbers. Then, and with respect to addition, that we'll also see. So 1 plus 2 plus 3 is same as 1 plus 2 plus 3. Right? So both are same. So associativity holds in set of natural number with respect to addition. Okay. Now, third one is existence of identity. So there exists an element E in G such that A star E is equal to A is equal to E star A. The element G is called as identity element. The element E here, not G. The element E is called as identity element, right? The element E is called as identity element. Now, for example, here the set of that element should be also in that set only. Okay, so if you see here, set of natural number with respect to addition. So, which element I have to add in that any natural number to get the same natural number? Which element I have to add to get the same natural number once again? So yes, it is 0. But 0, does it present in set of natural number? No. So there does not exist any identity element in set of natural number with respect to addition such that A star is equal to A is equal to E star A. Right? So here set of natural number addition with respect to addition is not, there does not exist any identity element. Now next is, here we can say, suppose set of integers with respect to addition. Yes, so set of integers with respect to addition, there exists an identity element with respect to addition, that is 0. 0 is present in set of integers. It means A plus 0 is equal to A is equal to 0 plus A, right? So there exists additive identity is 0. Whenever with respect to addition, it is called as additive identity. It is called as additive identity. Okay, now next, existence of inverse. An element of G possesses inverse, that is for all A belongs to G, there exists an element B belongs to G such that here A star B is equal to E is equal to B star A. Okay, here A star B is equal to E is equal to B star A. Then B is called the inverse of A with B is equal to A inverse. So A into A inverse is equal to identity and A inverse into star is equal to A. Now see here, for example, if you take the set of integers with respect to addition, so which element acts as an inverse for the set of integers? Okay, so which element I have to add in this A to get the 0? And that element also be present in set of integers. Yes, minus A. So minus A acts as an inverse, additive inverse for the set of integers. Here we are taking the special case, that is set of integers with respect to addition. So in the set of integers with respect to addition, minus A acts as an additive inverse. Okay, so minus A is called as inverse of A in set of integers with respect to addition. Okay, now next is special property, that is if G satisfies all these four properties: closure property, associative property, then existence of identity, existence of inverse, then G is said to be group. Now in addition, if G satisfies the commutative property, a group with commutative property is known as abelian group or commutative group. It is for all AB belongs to G. If A star B is equal to B star A, then star is commutative on set G. Right, now we'll see this example, set of integers with respect to addition. For AB belongs to G, for AB belongs to set of integers, then a plus b is same as b plus a. So it satisfies the commutative property. Therefore, set of integers with respect to addition forms an abelian group, right? Because any two integers, if you take any two integers, then addition of two integers is again an integer. So set of integers is closed with respect to addition. Associativity also holds. A plus b plus c is same as a plus b plus c. And existence of identity, here 0 belongs to z, acts as an identity element, and minus a belongs to z, acts as an inverse of z, right? So here we can see that set of integers with respect to addition forms an abelian group. Forms an abelian group. Now we will see the different example here in which this satisfies all this property. Now see, first, if G satisfies only closure property, then G is called as monoid. Okay, see here we will see, first we will write first closure property, second associativity, associative property, third one is existence of identity, fourth one is existence of inverse, fifth one is commutative property, commutative property here. No, closure property. Closure property, it means what? If G satisfies only closure property, then G is called as groupoid. Okay. And if G satisfies closure as well as associative property, then G is called as semi-group. Okay. And if G satisfies first, second, and third, closure property, associative property, and existence of identity, then G is called as monoid. Okay. And if G satisfies closure property, associative property, existence of identity, and existence of inverse, all the four properties, then G is called as group. Okay. And if G satisfies all the five properties, then G is called as abelian group. Okay, are you getting it? See, if G satisfies only closure property, what do you mean by closure property? For all A belongs to G, for all A and B belongs to G, then A star B also belongs to G. Associative property, for all A, B, C belongs to G, A star B star C is equal to A star B star C. And existence of identity, if there exists an element E in G such that A star E is equal to A is equal to E star A, then element E is called as an identity element. And existence of inverse, for every element of G possesses an inverse, that is for all A in G, there exists an element B in G such that here A star B is equal to E is equal to B star A. Then B is called as inverse of A, and we write B is equal to A inverse. So A into A inverse is equal to E, which is equal to A inverse into A. Right? So abelian group or commutative group. A group with commutative property is known as abelian group or commutative group. That is, for all AB belongs to G, if A star B is equal to B star A, then star is a commutative on G. Right? So we will see that here. Closure property, for if G satisfies only closure property, then G is said to be groupoid. If G satisfies closure as well as associative property, then G is said to be semi-group. And if G satisfies closure, associative, and existence of identity property, then G is called as monoid. And if G satisfies closure property, associative property, existence of identity, and existence of inverse, then G is called as group. And in addition, if G satisfies the commutative property, then G is called as abelian group. Okay. Now let's see. So we will see some examples depending on this. Suppose we will see here first one. So is n set of natural number with respect to addition forms a group? No. Why? Because there does not exist any identity element in set of natural number with respect to addition. It means 0 is not present in set of natural number. So therefore n with respect to addition is not a group. But n with respect to addition is a monoid. Sorry, is a semi-group. Is a semi-group. Right now, if we keep the same set and if you change the operation, binary operation here, if you take here multiplication, so n with respect to dot is, so multiplication of two natural number is again a natural number, therefore set of natural number is closed with respect to multiplication. Okay, closure property satisfied. Now a into b into c is same as a into b into c. So associativity also holds in set of natural number with respect to multiplication. Therefore, n dot forms a semi-group. Now, third one, in addition. So, which element acts as an identity element with the set of integers with respect to multiplication? Yes. So, which element I have to multiply for a belongs to n? There exists which element? To 1 in n such that a into 1 is equal to a is equal to 1 into a. Right? So there exists 1 belongs to n, which are also present in set of natural number. So n with respect to dot forms a monoid. Right? Now check whether their inverse exists or not. Okay. So for inverse, for all a in n, there exists which element in n such that a into that element gives you identity element. Right? So identity element is 1. So which element here? A into which element we will give, it gives you identity element. So here is 1 by a. But does 1 by a present in set of natural number? No. So there does not exist any b in n such that 1a into b is equal to 1. Right? A into b is equal to 1. So which implies n with respect to dot not a group. So only n satisfies the three properties, that is closure property, commutative property, associative property and existence of identity element. So therefore n dot is a monoid. Okay. Now third one, if I change the set, suppose if I take set of integers with respect to addition, then set of integers with respect to addition, just now we have seen it is an abelian group because all the properties of set groups, abelian groups are satisfied in set of integers with respect to addition. For example, if you take any two integers, then addition of two integers is again an integer. Second, associativity for A, B, C belongs to Z. A plus B plus C is same as A plus B plus C. So, associativity also holds in set of integers with respect to addition. So, which element acts as an identity element in set of integers? Yes, 0 belongs to Z, acts as an identity element in set of integers. Now, so which element acts as an additive inverse? Minus A in set of integers, right? So Z plus with Z with respect to addition forms a group, and it is also an abelian group. A plus B is same as B plus A. So Z plus is an abelian group, right? Now the fourth one, if I take set of integers with respect to dot, the operation will change. So set of integers with respect to dot. Now if you take here, so any multiplication of any two integers is again an integer. So closure property satisfied. Associativity 1 into 2 into 3 is same as 1 into 2 into 3. It means associativity also holds in set of integers with respect to multiplication, right? So Z dot is a semi group. Now Z with respect to addition, with respect to multiplication, which element acts as an identity element? Yes, 1. For any A belongs to, so there exists 1 in Z such that A into 1 is equal to A is equal to 1 into A, right? So there exists a identity element here, 1, which belongs to set of integers. So Z dot is a monoid, right? Now check whether it is group or not. So which element acts as an multiplicative inverse here? So 1 by a, but 1 by a does not present in set of integers, which implies z dot only forms a monoid, right? Z dot form is a monoid again. Okay, there does not exist any multiplicative inverse, right? Set of integers with respect to dot. Now, fifth set we will see set of integers with respect to subtraction. Subtraction is also a binary operation, right? Subtraction of any two integers is again an integer. So yes, it is a closure property also satisfied. But we can say here, suppose 1, 2, 3 belongs to Z. Then we will see 1 minus 2 minus 3. Here is minus 1 minus 3 minus 4. Okay. So here you can see again 1 minus 2 minus 3. 1 minus 2 minus 3. So 2 minus 3 is minus 1. Minus minus plus 1. So you will get here is 2. So associativity does not hold in set of integers with respect to subtraction. Therefore, Z with respect to subtraction is a groupoid. Is a groupoid. Okay, only closure property is satisfied. Yeah. So I hope you are getting it clear how to find out. And Z with respect to subtraction, set of natural number with respect to subtraction is not a groupoid also, because subtraction of any two natural number is not again a natural number. If you take 1 is a natural number, 2 is a natural number, then subtraction of 1 minus 2 is equal to minus 1 is not a natural number. Therefore, subtraction is also not a in set of integers, does not form at groupoid also. Okay, so no need to check whether it is group or not. So I hope you are getting it clear how to find out the, or how to show that whether it is group, semi-group, abelian group, monoid, groupoid. I have given every example of here. First is groupoid, which satisfies only closure property. Here is semi-group, which satisfied only closure and associative property. Here is monoid, which satisfied closure property, associative and existence of identity. Okay, and we'll see the group. And so one more example here, only group instead of abelian group. Okay, so which we will see. We can see which forms a group. Okay, so here we'll take suppose set of rational number. It is also a abelian group with respect to addition. Okay, set of any two rational number is again a rational number. So which is a which satisfy the closure property, and any three rational number associativity of these three rational numbers, that is a plus b plus c is same as a plus b plus c. So rational number property is also satisfied in set of with respect to addition in set of rational numbers. So associativity holds. Which element acts as an identity element with respect to addition? 0, which present in set of rational numbers, right? So set of rational numbers in that, so you will get 0 here also present. So set of rational number with respect to addition forms a monoid also. Then set of rational number with respect to addition, which element acts as an inverse, additive inverse? Minus a. For any a belongs to rational numbers, then minus a belongs to also rational numbers, and which gives you the so here set of rational number with respect to addition forms a group, right? And it is also a abelian group. Is an abelian group. Okay. Sixth one, set of real numbers with respect to addition is an abelian group, right? So there are many examples here we can see, which is group, monoid, then semi-group, abelian group, everything. Okay, now we'll see the next example. A special cases are here. Let Q plus be the set of all positive rational numbers, and star is a binary operation on Q plus. Okay, if Q plus, it means what? Set of all positive rationals. defined by A star B is equal to AB by 3 is an abelian group. So to show that is an abelian group, we have to show that all the five properties are satisfied. Okay, first property is closure property. First is closure property, right? So for that, for A, B belongs to G. So we can say that here A star B also belongs to G. Okay, so A star B is equal to what here? A star B is equal to AB by 3. As A and B belongs to here Q plus. Okay, so obviously A and B, A into B also belongs to Q plus with the set of positive rationals. So if A and B are positive rational, then A into B is also a positive rational. So AB by 3 is well defined, so it is also belongs to Q plus. Okay, it is well defined set, so therefore closure property satisfied in set of positive rationals with respect to the binary operation star. Okay, then second one, associative property. Associative property. For that we require three elements. For A, B, C belongs to Q plus. So we can see that here A plus A star. Here operation is given. A star B star C is equal to. So first we'll solve this B star C. How two elements are here, how star is operated on two elements B star C is equal to B into C by 3. B into C by 3. And how it is again defined? So here is A into B into C by 3 into 3, that is 9. Okay. Now here A star B star C. You can see here A star B is equal to AB by 3 star C. So A star B star A B C. So A star B is equal to AB by 3. So here is ABC by 3 into 3. A into B by 3, right? So here we will get ABC by 9. So from 1 and 2, right, associativity holds in Q plus with respect to star. Now we can write associativity holds in Q plus with respect to star. Okay. Now this is a special case, right? So we have to find out the identity element. So third property, existence of identity. Now it is not a regular binary operation, that is addition or subtraction. It is a different binary operation, that is star, right? So existence of identity, right? For A belongs to Q plus. So there exists E in Q plus such that A star E is equal to A. Okay, now we will find out E here, which element acts as an identity element. Okay, so how two elements are defined here, or how the star operation defined on two elements? A by 3 is equal to A. So if you see here, A is equal to 3A. So A get cancelled out. So here E is equal to 3, which is also present in Q plus. Acts as an identity element. Acts as an identity element in Q plus. Okay, acts as an identity element in Q plus. Now fourth one, okay, existence of inverse. There is existence of inverse. So for Here A belongs to Q plus. So there exists B in Q plus such that we have to find out that B, such that A star B is equal to identity, right? So here A star B, it means AB by 3 and identity is again 3, right? So here AB is equal to 9. So B is equal to 9 by A. As A belongs to positive, so 9 by A is also belongs to Q plus, which belongs to Q plus, right? So therefore 9 by A acts as an inverse for every element in Q plus, right? So therefore Q with respect to addition forms an group, forms a group, right? Now we'll see the next property, that is fifth one, commutative property. Commutative property. Yeah. See, for AB belongs to Q plus. Okay. So A star B is equal to, how we define, AB by 3. But A and B both are belongs to Q plus. So A into B is same as B into A by 3. So B into A by 3, it means B star A. So commutative property also holds in set of positive rationals with respect to defined operation star. Therefore, Q plus with respect to defined operation star forms an abelian group. That is, we want to show that. Okay. I hope you are getting it clearly how to show that the given set Q plus with the set of positive rational forms an abelian group. Okay. Now, move further. Now see, the set of the set 2i of all even integers with 0 is an abelian group with respect to addition. So set of all positive rationals, set of all positive, even positive integers forms an abelian group, okay, with respect to addition, that we will see here. So first property, closure property. Closure property for AB belongs to 2i, right? Both are even integers, so addition of two even integers is again a even integer. Then therefore A plus B is also belongs to 2i, right? So therefore, as addition of two, since addition of two even integers is again even integer. Okay? Second one, associative property. Associative property for A, B, C belongs to 2i, then A plus B plus C. So A plus B is same as A plus B plus C, because 2i is a subset of I, set of even integers, because associativity holds in set of integers and set of even integers is a subset of integer. So obviously associativity holds in set of even integers with respect to addition. Okay. Now third one, existence of identity. Existence of identity. Okay. For A belongs to 2i. So there exists 0 belongs to 2i such that A plus 0 is equal to A is equal to 0 plus A. So 0 belongs to 2i acts as an identity element for set of even integers. Okay. Now fourth one, existence of inverse. Okay. For A belongs to Q plus. sorry, A belongs to 2i, I'm sorry. A belongs to 2i. There exists which element? Here, B in 2i such that A plus B is equal to identity, but identity is 0. So A plus B is equal to 0, so which implies B is equal to minus A. It also belongs to 2i, right? So because it is an integer. So therefore, B is equal to minus A acts as an inverse for every element in set of even integers. Okay. Now fifth one, commutative property. Commutative property here. For AB belongs to 2i, then A plus B is same as B plus A. Hence addition is commutative in, hence addition is commutative in set of integers, set of even integers. Therefore, set of even integers with respect to addition forms an abelian group. Forms an abelian group. Okay. Now, next. The set Q1. Okay. The set Q1 of all rational numbers other than 1. Okay. With operation star defined by A star B is equal to A plus B minus AB is an abelian group. Q1. It means here we will see the set Q1 of all rational numbers. It means other than 1. Okay. With the defined operation A star B is equal to here A star B is equal to A plus B minus AB forms an abelian group. So let's start. For that, first is closure property. Closure property for we require two elements AB belongs to Q1, which implies A and B both are other than 1, right? So that is A is not equal to 1 and B is not equal to 1. A and B both are other than 1, right? Now we'll see that. So as A star B is equal to A plus B minus AB, which is a well defined, which also belongs to Q1, which is other than 1. As A and B are other than 1, then definitely these are also other than 1 because it is a well defined operation. So therefore, star is closed in Q1, right? So associativity hold, closure property holds. Then second is associative property. Second, associative property. Okay, for that we require three elements. For A, B, C belongs to Q1. It means A is not equal to 1, B is not equal to 1, C is not equal to 1. Right? So we'll see here A star B star C, which is equal to A star B is defined as A plus B minus AB star C. Right? So here you will get now this is your A and this is your B. So A plus B, it means A plus B minus AB plus C minus A into B. So here A plus B minus AB into C, right? So you will get here A plus B plus C minus AB minus A minus B minus minus plus AB, right? So A plus B plus C minus AB, sorry, minus AC minus BC plus ABC, right? So you will get this. So obviously it is belongs to, now see we calculate also A star B star C. If both are same, then associativity holds. So A star B star C, it means B plus C minus BC, right? So here A star B, it means here A into B. So A plus B plus C minus BC minus B. Here A star B, it means A plus B plus C minus AB. So minus A into B plus C minus BC. So after multiplying, you will get A plus B plus C minus BC minus AB minus AC minus minus plus ABC. Now if you observe, this is 1, this is 2. From 1 and 2, both are same. So if RHS are same, then obviously LHS are same. So associativity also holds in Q1 with respect to star. Okay. Now third one, existence of identity element. Existence of identity element. So for A belongs to Q1, there exists E belongs to Q1 such that A star E is equal to A, right? As A belongs to Q1, E belongs to Q1. So obviously A is not equal to 1, E is not equal to 1. Both are other than 1, right? So we have to find out the value of E. So define the operation star on A and E. So here A star is A plus E minus A into E is equal to A, right? So you will get here E minus A plus A, this will get cancelled out, is equal to 0, right? So you will get E into bracket 1 minus A, which is equal to 0. As E is not equal to C, which implies here A is other than A is not equal to 1. So to get this 0, so obviously A is not equal to 1. So this means this is not 0. So which implies E must be 0, right? So identity element E is equal to 0 here. So 0 belongs to Q1 other than 1A. So therefore E is equal to 0 acts as an E is equal to 0 acts as an identity element. E is equal to 0 acts as an identity element. Okay. Now fourth one, existence of inverse. Here. Okay. So for A belongs to Q1, there exists B in Q1 such that A star B is equal to identity, right? So here A star B is equal to identity. As AB belongs to Q1, A is not equal to 1, B is not equal to 1, right? A star B, it means A plus B minus AB and identity element is 0, right? So we have to find out the value of B. So here B into bracket 1 minus A is equal to minus A, right? So B is equal to minus A upon 1 minus A. So obviously it is well defined since A is not equal to 1, right? So minus A belongs to minus A upon 1 minus A belongs to Q1, acts as an inverse for A in Q1. Clear? Are you getting it? B is equal to minus A upon 1 minus A belongs to Q1, acts as an inverse of A B is act is an in B is equal to this is an inverse of A in Q1. Okay. So Q1 with respect to star forms a group. Okay, we'll check whether it is abelian or not. Okay, for all AB belongs to fifth one. For all AB belongs to Q1, it means A is not equal to 1, B is not equal to 1. Then A star B. Okay, so A star B is equal to A plus B minus AB. So can I write this as same as B plus A minus BA? So is it nothing but B star A? Yes, commutative property also holds in Q1 with respect to defined operation star. Okay, so therefore Q1 with respect to star forms an abelian. Okay, I hope it is clear to you how to show that the given set is an abelian group. Okay, now this is different example. I am taking all the different examples and it will clear everything here. Now G is equal to A plus B root 2. Now the element in the set G is written in the form of A plus B root 2 where A and B belongs to Q. Then G plus is an abelian group. Okay, so for AB belongs to G. Okay, so for closure property we will see one here. Okay, closure property. Okay, for we require two elements for to prove the closure property for AB belongs to G. But how we are written in the element in the set G where A and B belongs to Q. AB belongs to G. Then we will see here. We'll take the other elements. Suppose for X and Y belongs to G, right? And A1, B1, A2, B2 belongs to Q. Why? Because every element X and Y belongs to G can be written in the form of A plus B root 2. So we can write X is equal to A1 plus B1 root 2 and Y is equal to A2 plus B2 root 2, right? X is equal to A1 plus B1 root 2, Y is equal to A2 plus B2 root 2, right? Or AB belongs to Q. So A1, B1, A2, B2 belongs to Q. Now we'll see check the addition of these two elements. So X plus Y, which is equal to A1 plus B1 root 2 plus A2 plus B2 root 2, right? Now here we can say A1 plus, you take the real parts, A1 plus A2 plus B1 plus B2 into root 2. Again the element in this same form. So again these elements belongs to G. Why? Since A1, A2 belongs to Q, B1, B2 belongs to Q, and set of rational number, just in the previous example we have seen. So addition of any two rational number is again a rational number. So A1, A2 is also a rational number. A1 plus A2 is also a rational number. B1 plus B2 is also a rational number, and it is the elements is in the form of A plus B root 2 form. So obviously it is belongs to G. Therefore G is closed with respect to addition. Okay. Therefore, G is closed with respect to addition. Okay. Now, for the associativity, second one, associative property. Associative property. For that, we require three elements. So, for X, Y, Z belongs to your G. Okay. So, every element can be written. So, here A1, B1, A2, B2, A1, B1, C1, A2, B2, C2, A3, B3, C3 belongs to Q, right? And we know that addition of any two rational numbers is again a rational number. So associativity also holds in set of rational number. So obviously that also present in the set G. Okay, so the elements of G are rationals and the addition of rationals is associative. Therefore, it is associative. Okay, therefore associativity holds in G with respect to addition. Okay. Now the very important, that is existence of identity. So how to find out the identity element? Existence of identity. Okay. So for X belongs to G. Okay. So or we can say that A plus B root 2. Okay. A plus B root 2 belongs to G. Then there exists E in G such that A plus B root 2 plus which element gives you the same element. Okay? So this will gives you E is equal to A plus B root 2 minus A plus B root 2. Right? So is it nothing but A minus A, it means 0, plus B minus B, it means 0 root 2. So E is equal to 0 plus 0 root 2. So you don't write here only 0. Right? You have to write it here 0 plus 0 root 2. Otherwise it will be a wrong. Because not only 0 is the identity element, here 0 plus 0 root 2 is the identity element. Okay, so 0 plus 0 root 2 belongs to G, acts as an identity element with respect to addition. Now third one, fourth property is existence of inverse. Now for A plus B root 2 belongs to G, there exists, here we will see that there exists minus A minus B root 2 belongs to G such that A plus B root 2 plus minus A minus B root 2 is equal to 0 plus 0 root 2. Right? A minus A 0, B minus B 0 into root 2. So A minus B root 2 belongs to G, acts as an inverse for the every element of A plus B root 2 in that G. Okay? Therefore, G plus is a group because all the four properties are satisfied: closure, associative, existence of identity, and existence of inverse. Okay, now fifth one, commutative property. Commutative property. Okay. For A B belongs to for we can say that xy belongs to G. For xy belongs to G, x is equal to a1 plus b1 root 2, y is equal to a2 plus b2 root 2. Okay. Then we can say that x plus y is equal to here x plus y is equal to a1 plus a2 plus b1 plus your b1 plus b2 root 2. Right? So get here a2 plus a1 plus b2 plus b1 root 2. Right? So can I write this as a2 plus b2 root 2 plus a1 plus b1 root 2. But this is nothing but y plus x. So there hence G plus is an abelian group. G plus is an abelian group. Now next, very important, let R is equal to the other type of example. R is equal to 0 degree, 60 degree, 120 degree, 180 degree, 240 degree, 300 degree, and is equal to the binary operation, so that star, and star is a binary operation, so that A and B in R and A star B is overall angular rotation corresponding to successive rotations by A and then by B, show that R star is a group. Okay, show that R star is a group. So for that we have to find out the angular rotation for every element for this group. So angular rotation by 60 degree, right? So we can see that here. Angular rotation by 60 degree. There is star. 0 degree, 60 degree, then 120 degree, because angular rotation by 60 degree, therefore the next rotation will be 60 degree, then 180 degree, then 240 degree, and 300 degree. And next is 360 degree, but 360 degree is nothing but the 0 degree, right? Now there is 0 degree, 60 degree, 120 degree, 180 degree, 240 degree, 300 degree, right? Here is 180 degree, 60 degree, 190, 120 degree, 180 degree, 240 degree, and 300 degree. Now see here, angular rotation. So 0 degree plus 0 degree. So you will get 0 degree, right? 0 plus 60 degree, that is 60 degree. Finite set hai. We can do the composition table. So 0 plus 120, 120. So 0 plus 180, 180, 240, and 300. Now next is 60 plus 0, 60. 60 plus 60, 120. Okay. So here is 180. Here is 240 degree. Here is 300 degree. Now 360 degree, it means 0 degree. Right. 120 degree, 180 degree, 240 degree. Here is 300 degree. Then 60 degree. Here is 0 degree. And here is 60 degree. Right. So 180 degree plus 240 degree. Here is 112 plus 300 degree, then 0 degree, 60 degree, 120 degree. Right? Here is 240 degree, here is 300 degree, then 0 degree, 60 degree, 120 degree, 180 degree. Right? So here is 300 degree, 0 degree, 60 degree, 120 degree, 180 degree, and 240 degree. Now this is your angular rotation. Okay, this is your angular rotation of the given set G. Now we'll say that whether the set is closed. Now how to check whether the set is closed or associative property holds or not? Okay, by using composition table, it's very simple. So here we can see the closure property first. Closure property. So there are two different methods. You can take any two elements and say that the star operation is again a. So here is the star operation. So A star B. So 0 star 60 degree, same as 60 degree, right? So you can take any two elements. So from the composition table, if you observe, all the elements from the set, given set are only. Okay. So from the given set are only. Therefore, R is closed with respect to star. Okay. So we can write by using composition table. For either you can write down any two elements. For 60 degree, 120 degree belongs to R. Then 60 degree of star 120 degree is equal to 180 degrees also belongs to R. Right? So therefore the composition table. From the composition table, so given set R is closed. R is closed with respect to star. If there is at least one element which is not present in the given set R, then this set will not be a closed, right? But here every element from the composition table, this is known as composition table. Sorry, every element of the set R is the composition table. Every element from the composition table from the set R only. Therefore, the set R is closed with respect to the defined operation star. Okay. Now associativity, we can say that obviously you can say that from the composition table here, 0 degree plus 60 degree plus 120 degree is equal to, you will get 180 degree. Similarly, 60 degree plus 120, 0 degree plus 60 degree plus 120 degree is same as 180 degree, right? So associativity also belongs to, here we can say that associative property. Second, You can write that associative property for A, B, C belongs to R. For A, B, C belongs to R. Here not real number, only set R. Then here A is equal A star B star C is same as A star B star C. Right? So here we will take A is equal to, suppose here A is equal to 120 degree, B is equal to 180 degree and C is equal to 60 degree. Then we'll say A star B star C. Okay, so we'll consider A star B star C is equal to A is 120 degree star 180 degree star 60 degree, right? But 120 degree star 180 degree star 80 degree is 240 degree, right? 120 degree plus 240 degree is 360 degree, which is 0 degree, right? Now from A star B star C, 120 degree plus 180 degree star 60 degree. 120 degree plus 180 degree is 300 degree star 60 degree. So it is 360 degree, right? But which is nothing but 0 degree. So associativity also holds in R with respect to the star, right? Associativity, associativity holds in R with respect to star. Therefore, here R with respect to star forms a semigroup. Now third one, existence of identity. Existence of identity. Now very simple trick I am telling you here. So because of which element gives you the exactly similar row here, the first row. So 0 gives you the exactly similar row here. Therefore 0 degree acts as an identity element. Right? Very simple way to find out the identity element here. So which element acts as an identity element? So here 0 gives, मतलब यहाँ पे हम लोग 0 दे रहा है exactly similar row, right? So that it imply 0 acts as an 0 degree acts as an identity element. Okay. So for all A in R, we can say for all A in R, there exists 0 degree in R such that A star 0 is equal to A degree. A degree star 0 degree is equal to A degree. Okay. So this is your identity element. Okay. Now fourth one. Now for the finite set, we have to find out every inverse for every element in R. Okay. Now see how to find out the inverse of it. Now, which is the inverse? Now, which element is operated on this element to give the identity element? So, 0 degree star 0 degree gives you 0 degree. That is identity element. Now, 0 degree, 60 degree star 300 degree gives you 30 degree. So, what is the inverse of 0 here? For all A belongs to R, there exists B in R such that A star B is equal to 0 degree. A degree star B degree is equal to 0 degree. Right? So A degree star B degree is equal to 0 degree. This will gives you the inverse of A. Now see, for we have to find out the inverse of. So 0 degree inverse is equal to 0 degree. Now 60 degree inverse is equal to, now which element gives you the inverse of 60 degree? So 60 into which? So 60 star, here we'll see that 60 star 300 gives you 0 degree. So inverse of 60 degree is 300. Okay. Now inverse of here 120 degree. 120 degree inverse is equal to. So which element gives you 120 degree inverse is 240. 120 degree inverse of 220. Here inverse of 120 is 240. Inverse of 120 is 240. Now inverse of 180 is, see here, inverse of 180 is 180. Right? Inverse of 240 is equal to, inverse of 240 is equal to 120. Right? Inverse of 300 is equal to, inverse of 300 is equal to 60. Right? The inverse exists for every element in set R. Therefore, R with respect to stars forms a group. Therefore, R with respect to star forms a group. Okay, I hope you are getting it clear. Now see the next example. The defined operation is different. Okay, so here let G be the set of all non-zero real numbers. Here, let G be the set of all non-zero real numbers, and let A star B is equal to AB by 2. Show that G star is an abelian group. Right? So, first of all, first property, closure property. Closure property. Now it's very simple. Closure property for AB belongs to G. Okay, A star B is defined as AB by 2. A and B are non-zero, so A into B is also non-zero. So G is closed for all AB belongs to G. A star B is also belongs to G, as it is well defined set. So definitely G, therefore G is closed with respect to star. Okay. Now second property, associativity. Associative property. Okay. For A, B, C belongs to G. Okay. Now, as A, B, C belongs to G, so we'll see that A star B star C is equal to, but A star B star is operated on elements of G is A star B is equal to AB by 2. Right? So here we can write AB by 2 star C, it means ABC by 4, 2 into 2. Okay. Now we'll check A star B star C. A star B star C, it means BC by 2. So A star BC by 2, it means ABC by 4. 2 into 2. Right? So here from these two, LHS are RHS are equal, so which implies LHS are also equal. Therefore, associativity holds in G with respect to star. Okay. Now see. Next is existence of identity. Third, existence of identity for A belongs to G. There exists E in G such that A star E is equal to E star A is equal to A. Right? So here we will consider, here we have to find out E. So A star E is equal to A. But how the star operation operated on elements of G? So A star is equal to A by 2, which is equal to A. Right? So AE is equal to 2A. So A get cancelled out, E is equal to 2. Exactly similar to as we have seen in the example number 1, I think. Okay, so E is equal to 2, but 2 is also present in, whereas A is not equal to 0, so A cancel out. So E is equal to 2. Okay, so which belongs to G. So E is equal to 2. Therefore, 2 is the identity element of G with respect to star. Therefore, 2 is the identity element of G, identity element of G with respect to star. Okay. Third one. Fourth one, existence of inverse. Existence of inverse. Okay. For let A belongs to G, let A belongs to G, there exists B in G such that A star B is equal to identity. Right? We have to find out B. So how that it is operated? AB by 2 is equal to E, but E is 2. So AB is equal to 4. So which implies B is equal to 4 by A, since A is not equal to 0. So this is well defined. So B is equal to 4 by A belongs to G. So this acts as an inverse of A. Okay. Now we'll see the commutative property. Commutative property. Okay. For AB belongs to G, consider A star B is equal to, here AB by 2. The same we can, as A and B are non-zeros, so we can write then BA by 2, so which is nothing but B star A. Therefore, commutative property also holds in G with respect to star. Hence, G with respect to star forms an abelian group. Forms an abelian group. Okay. Now next. Now very important property, that is addition modulo M. So what you mean by addition modulo M? A new type of addition is defined as addition modulo M, and it is denoted by this. Here it is denoted by addition modulo M. Okay, and written as A addition modulo B M, where A and B are any integers and M is a fixed positive integers. Hence, A addition modulo M B is equal to R, where 0 less than or equal to R less than M. Okay, now for example, we will see 2 addition modulo 8 4. Okay, 2 addition modulo 8 4. Since we have to write down here remainder. So first do the usual addition, divide by 8 and write down the remainder. Okay, so here 2 plus 4 8. Sorry, 2 plus 4 6. 6 divided by 8. Now see here. So here 0. So remainder is 6. So 2 addition modulo 8 4 is equal to 6. Okay, exactly similar way we can write. Suppose 4 here, 4 addition modulo 7 8 is equal to. So first of all add these two. 7, 8 plus 4 12. 12 divided by 7, right? 12 divided by 7. So 7 ones are 7. Remainder is 5. So write down that. I hope you are getting it clear. How we write the addition modulo. First add these two, divide by 7 and write down the remainder. Suppose 2 addition modulo 3 5. So 5 plus 2 7. 7 divided by 6. So remainder is 1. Right? So 18 addition modulo 2 4. So you will get 18 plus 4 22. 22 divided by 2. That is 11. Remainder is 0. I hope you are getting it clear how to write the addition modulo M. Okay. Exactly similar way here, congruent modulo M. When A and B are two integers such that A minus B is divided by a fixed positive integer M, then we write that A is congruent to B modulo M. 3 equal sign. So A congruent to B modulo M. Okay. So when we say that these are congruent when M divides A minus B. For example, suppose here we'll take any example. 4 is congruent to 2 modulo 2. It means 2 divides 4 minus 2. 2 divides 2. Okay. Therefore 4 is congruent to 2 modulo 2. Here 5 is congruent to 3 modulo 4. Is it, see, 5 minus 3, that is 2, but 2 is not divisible by 4. So 5 is not congruent to 3 modulo 4. Are you getting it? Here see, 7 is congruent to 5 modulo 2, right? So 7 minus 2 divides 7 minus 5. Yes, 2 divides 7 minus 5. Therefore 7 is congruent to 5 modulo 2. I hope you are getting it clear by what you mean by congruent. Okay. Now, multiplication modulo m, exactly similar to addition. First to multiply these two numbers, integers, and then divide by m and write down the remainder. Okay. For example, here 5 multiplication modulo 7, 6. So 6 5s are 30. When 30 divided by 7, so remainder is 2. Right? 4 multiplication modulo 5, 6. So 6 5, 4s are 24. 24 divided by 5. So remainder is 4. Yeah. So 18 more multiplication modulo 5, 3. 54. 54 divided by 5. So you will get when 54 divided by 5, the remainder is 4. Okay. I hope you are getting it clear. Now, 8. Next example by using the addition modulo 8. Now here the combination of composition table and addition modulo 8. Okay, so addition modulo 8 is an abelian group. So this is a finite group. So whenever it is a finite group, we'll prepare a composition table. Okay, so let's see here. Get on next page. Addition modulo 8. है ना? Number 0, 1, 2, 3, 4, 5, 6 and 7. 0, 1, 2, 3, 4, 5, 6 and 7. This is your composition table, but for the operation addition modulo 8, right? So 0 plus 0 divided by 8 is 0, 1, 2, as it is 3, 4, 5, 6, 7. You can do 1 plus 0, 1, 2, 3, 4, 5, 6, 7. But 8, when divided by 8, remainder is 0, 2, 3, 4, 5, 6, 7. 8 divided by 8, 0. And 9 divided by 8, remainder is 1. 3, 4, 5, 6, 7, 0, 1, 2. Right? 4, 5, 6, 7, 8. 8 divided by 8, remainder is 0. 9 divided by 8, remainder is 0. 10 divided by 8 and 11 divided by 8. Right? So here is 5, 6, 7, 0, 1, 2, 3, 4. 6, 7, 0, 1, 2, 3, 4, 5. 7, 0, 1, 2, 3, 4, 5, 6. I hope you are getting it clear. Just add these two numbers and divide by 8. Write down the remainder. Okay. Now, if you observe, all the entries from the composition table are the set G only. Therefore, G is closed with respect to addition modulo 8. We can write in this way also. Closure property here. Obviously from the table, all the elements from the set G only. Therefore, G is closed with respect to addition modulo 8. Okay. Second one, associative property. Associative property. Okay. Now, obviously from the table, for example, suppose 7, 2, 3. If you take 7, 2, 3, then 7 addition modulo 8, 2, addition modulo 8, 3. So 7 addition modulo 8, 2, it means 9 divided by 8, remainder is 1. Addition modulo 8, 3, 3, 1, so here is 4. Okay. So 7 addition modulo 8, 2, addition modulo 8, 3. So you get 2 plus 3, 5. 5 divided by 8. Okay, so remainder is, that's 780. 5 divided by 8, remainder is 5. So 7 plus 5, 12. 12 divided by 8, remainder is 4. So associativity also holds in set G with respect to addition modulo 8. Okay. Now, let's see here. Third one, existence of identity. Existence of identity. Okay. For A belongs to G, there exists which element acts as an identity element? Which element gives you exactly similar row? 0. So 0 acts as an identity element. There exists 0 in G such that A plus 0 is same as 0 plus A is equal to A. Okay. Now fourth one, we have to find out the inverse for every element. So existence of inverse. Okay. For now here we'll see the 0 inverse of 0 is 0. Right? 0 inverse is equal to 0. Now next is inverse of 1. 1 because of 7. So 1 inverse of 1 is 7. Okay. Now inverse of 2. The inverse of 2 is 6. Inverse of 2 is 6. Right? Inverse of 3. क्या आएगा? Inverse of 3 will be 5. 5 plus 3, 8, and 8 divided by 8. That is 0. Inverse of 4, that is, here you will get inverse of 4 is 4. 4 plus 4, 8. Inverse of 5 is 3. Inverse of 6 is 2. And check it here. Inverse of 6 is 2. Inverse of 7 is 1. Right? Inverse of 7 is 1. So inverse exists for every element in set G. Therefore, G forms a group with respect to addition modulo 8. Okay? Hence, every element possesses inverse. Therefore, G with respect to addition modulo 8 forms a group. Now commutative property. Commutative property for here for 4 addition modulo 8 3 is equal to 4 plus 3 7 divided by 7 and 3 addition modulo 8 4 again 7. So obviously commutative property also holds in G with respect to addition modulo 8. Therefore, G with respect to addition modulo 8 forms an abelian group. Okay. Next one, see here, ninth one, that is G is equal to 1, 2, 3, 4, 5, 6, 7. Multiplication modulo 7, and multiplication modulo 7 is, here we will see whether it is forms a group or not. Okay, so here multiplication modulo 7, so we are not taking 0 in that with respect to multiplication. Okay, so we'll take only the non-zero elements here. We will get the non-zero elements. G contains multiplication modulo 7, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So here 1 into 1, 1, 1 into 2, 2, 3, 4, 5 and 6, because 6 into 1, 6 divided by 7, remainder is 6. Now 2 into 1, 2 divided by 7, 2, 4 divided by 4 divided by, oh sorry, 2 into 1, 2 divided by 7, remainder is 2. 3 into 2, 6 divided by 7, remainder is 6. 2 into 4 divided by 7, remainder is 1. 2 into 5, 10 divided by 7, remainder is 3. 2 into 6, 12 divided by 7, remainder is 12, it means 5. Right? 3 into 1, 3. 3 into 2, 6. 6. 3 into 3, 9 divided by 7, remainder is 2. 3 into 4, 12, remainder is 5. 3 into 5, 15 divided by 7, remainder is 1. 3 into 6, 18 divided by 7, remainder is 4. Right? Now 4 into 1, 4. 4 into 2, 8 divided by 7, remainder is 1. 4 into 3, 12 divided by 7, remainder is 5. 4 into 4, 16 divided by 7, remainder is 2. 4 into 5, 20 divided by 7, remainder is 6. 4 into 6, 24 divided by 7, remainder is 3. 5 into 5, then 5 into 2, 10. 10 divided by 6, 4. 5 into 3, 15. Oh, sorry, not 4, here is 3 divided by 7. No? 5 into 3, 15. 15 divided by 7, remainder is 1. 20 divided by 7, remainder is 6. 25, 4. 30, remainder is 2. 6. 6 into 2, 12. 5. 6 into 3, 18. 4. 6 into 4, 24. 24 divided by 7. So 24 divided by 7, remainder is 3. 6 into 5, 30. So remainder is 2. 36, remainder is 1. I hope you are getting it clear how to draw the composition table. Now check whether it is group forms a group or not. Okay. All the elements from the composition table from the set G only. Therefore, G is closed with respect to multiplication modulo 7. Now, associativity also holds. You can check here 3 multiplication modulo 7, 2 is same into 3 is same as. So, we can see here closure property. First, closure property. Okay. So, it holds obviously from the table. All the elements from the table from the set G only. All the elements from the table are from the set G only, are from set G only. Therefore, G is closed. G is closed with respect to multiplication modulo 7. Right? Second one, associative property. Associative property. Obviously from the table 3 multiplication modulo 7, 5. multiplication modulo 7, 4 is equal to 3 into 5, 15, 15 divided by 7, 1, 4 into 1, 4, 4. So 3 multiplication modulo 5, 5 fours are 20, 20 divided by 7, 6, 18, and 18 divided by 7, that is 4. Obviously, associative property also holds. Which element acts as an identity element? So 1 gives you exactly similar row. So for 1 belongs to G, third one, for 1 belongs to G, acts as an multiplicative identity. Okay, so that is with respect to multiplication modulo 7, right? So for A belongs to G, there exists 1 in G such that A multiplication modulo 7, 1 is equal to A. Okay. Now fourth one. Now check whether inverse exists or not. The inverse of 1 is 1. Inverse of 2 is 4. Inverse of 3 is 5. Inverse of 4 is 2. Inverse of 5 is 3. Inverse of 6 is 6. So we can write here inverse exists for every element. Right? So 1 inverse is equal to 1. 2 inverse is equal to 4. 3 inverse is equal to 5. 4 inverse is equal to 2. 5 inverse is equal to 3. And 6 inverse is 6. Okay, so inverse exists for every element. So therefore, G with respect to multiplication modulo 7 forms a group. Now commutative property, fifth one, commutative property for AB belongs to G, then A multiplication modulo B is same as B multiplication modulo A. Okay. So obviously from that 3 multiplication modulo 2 is equal to 3 into 2, 6 divided by 6, right? And 2 multiplication modulo again is 6. So commutative property also holds. Therefore, P with respect to multiplication modulo 7 forms an abelian group. Forms an abelian group. The last one is here the set of residue classes modulo n. This symbol is denoted for residue class of Z. Okay, so here Z6 is the residue class, be the set of Z6 be the set of residue classes modulo 6. Residue classes modulo 6. Okay, so that is Z6 is equal to here singleton 0, singleton 1, singleton 2, singleton 3, singleton 4, singleton 5, right? Now we'll find out the composition table. Again, here are the finite number of elements. Prepare the composition table with respect to addition. 0, singleton 1, singleton 2, singleton 3, singleton 4, singleton 5, right? Singleton 0, singleton 1, singleton 2, singleton 3, singleton 4, singleton 5, right? So 0 plus 0, 0, 0, 1, 2, 3, 4, 5. Right? Here is 1, 2, 3, 4, 5. 6. 6 it means 0. Right? 2, 3, 4, 5. At 6 it means 0. 7 it means 1. 3, 4, 5. 6 it means 0. 1, 2, 4, 5. 6 it means 0. There is 1. There is 2. There is 3. There is 5. There is 0. There is 1. There is 2. There is 3. There is 4. Okay. So you can see that here all the entries from the composition table from the set Z6 only. Okay. So obviously it is closed with respect to addition. So Z6 is closed with respect to addition. From closure property, all the entries in the composition table from from the set Z6 only. Therefore, Z6 is closed with respect to addition. Associative property. Associative property. Okay. For ABC belongs to singleton 1, singleton 4, singleton 5 belongs to Z6. Right? So we can see that associativity singleton 1 plus singleton 4 plus singleton 5 is equal to singleton 1 plus 5 plus 4, 9. So here is 3. Right? So which will give you here is 4. Right? Now here singleton 1 plus singleton 4 plus singleton 5. Singleton 5 plus singleton 5. 10 divided by 6. Here is 4. Okay. So associativity holds. So which element acts as an identity element? 0, because 0 gives you exactly similar row here. Okay. So 0 belongs to Z6. Existence of identity. 0 belongs to Z6. Acts as an identity element. Acts as an identity element. Okay. Fourth one, existence of inverse. Existence of inverse. You can see that inverse exists for every element. Inverse of 0 is 0, inverse of 1 is 5, inverse of 2 is 4, of 3 is 3, inverse of 4 is 2, inverse of 5 is 1. Okay. So inverse of 0 is 0, inverse of 1 is 5, inverse of 2 is 4, inverse of 3 is 3, inverse of 4 is 2, inverse of 5 is 1. Okay. So inverse exists for every element inside G. Therefore, G with respect to Z6 with respect to addition forms a group. Okay. Now abelian also we can see that the row entry and column entry are same 0 1 2 3 4 5 0 1 2 3 4 5 1 2 3 4 5 0 2 4 5 0 2 3 4 5 0 1 2 3 4 5 0 1. So row and columns are same, so it shows that commutative property also holds. Commutative property holds. Commutative property also holds. Okay. Therefore, Z6 with respect to addition forms an abelian group. Okay. That's it. We have to prove. To prove that it is an abelian group. So everything we prepare a composition table where Z6 is the residue classes modulo. Okay. So in this lecture we have clear all the properties of the groups, abelian groups. Okay, in the next lecture we will see the permutation group, also the subgroups and cosets, then your cyclic groups, everything we will see in the next lecture, then isomorphism of groups and everything. Okay, so tomorrow I will be here at the same time with the, see, we have covered many examples here, almost 10 to 11 examples we have covered. So every concept is clear here with the help of examples. Okay, group, what do you mean by group? Then how to find out the identity element and inverse element of the uh, different defined operation. Okay, that every part is covered here. You can go through it. Okay, so I will be here in the same time tomorrow at 11:15 with the new terms of groups, that is isomorphism of groups, subgroups, cosets, and here we will see cyclic groups. Okay, different types of groups also we will cover. Now the most important thing I'm going to tell you, from Monday onwards I will be in the Unacademy's next new channel, that is Unacademy semester exam channel. I will be available from the Monday at the same time. Thank you so much. If you are liking my videos, please do like, share and subscribe. Have a good day.